Last time we talked about how the electron configuration, or the arrangement of the electrons energetically in an atom, determined all the chemical properties of that atom. Well, then it makes sense that the electron configuration influences atomic size and other things. So let's take a look at that a little more closely. I thought it was kind of interesting, this quote by Richard Feynman. He's a famous physicist. He said that if in some cataclysm all scientific knowledge were to be destroyed and only one sentence passed on to the next generation of creatures, what statement would contain the most information in the fewest words? I believe it is the atomic hypothesis, that all things are made of atoms, little particles that move around in perpetual motion, attracting each other when they are a little distance apart, but repelling upon being squeezed into one another. In that one sentence, you will see an enormous amount of information about the world, if just a little imagination and thinking are applied. So it's kind of neat. We're studying the gist of the universe here, according to Dr. Feynman. Atomic radius trend. So here's our periodic table, and just where is the largest atom in the periodic table? Right down here. That's the largest. What is that? Francium. Where's the smallest? Up here. That's helium. So draw an arrow from the smallest to the largest. There. Increasing atomic radius. How about this one? Electrons in outer lying atomic orbitals feel an effective nuclear charge. That is what? Than electrons that are closer to the atoms. Less than. So the idea behind this is that there's a lot of electron between the outermost electron and the nucleus. So those outermost electrons, they're shielded by the inner electrons. So those outer electrons don't feel the full positive force of that nucleus because they're being shielded by those inner electrons. Ionization energy trend. What is ionization energy? That's just the energy it takes to remove an electron. The energy to remove one electron from an atom. Write an example atomic ionization reaction for a sodium atom. Also, sodium has to lose one electron. What's left? A sodium ion. Sketch an arrow from smallest to largest ionization energy. So, since this was the biggest, he's going to have the smallest ionization energy. Very easy to ionize because it is so big. Helium has the largest ionization energy because it's so small. So if we want to draw an arrow from smallest to largest ionization energy, it's the opposite of size. Electron affinity. What's electron affinity? Write an example of electron affinity reaction for a chlorine atom. Electron affinity is grabbing onto one electron. What's the energy? So if chlorine grabs an electron, the two reactants would be a chlorine atom and an electron. What would they make? Chloride anion. Sketch an arrow from smallest to largest electron affinity. So for electron affinity, it increases going this way. We pretty much stop right at the nobles. So here, electron affinity increases, going from left to right across the periodic table. The electronegativity trend. What is electronegativity? Let's say we have element A and we have element B. And we are going to make a chemical bond between the two. The makings of a molecule here. Well, it turns out there's a tug of war between atom A and atom B for the electrons in that chemical bond. And whoever wins this tug of war is the most electronegative. So electronegativity is the tendency for an element to attract electrons. So the stronger it is at that tug of war game with electrons, the more electronegative it is. So sketch an arrow from the smallest to largest electronegativity. Fluorine, so again, this is going to stop at the noble gases here. Fluorine is the most electronegative element on the planet. Number 1. We'll draw a diagonal arrow to fluorine, increasing electronegativity. Isoelectronic. What does isoelectronic mean? All it means is that you have two atoms of different elements with the same electron configuration. Two atoms of different elements with the same electron configuration. Well, how can you do that? Let me give you an example of two isoelectronic atoms. Helium. Helium is 1s2. Lithium is 1s2, 2s1. Now, if I want helium and lithium to be isoelectronic, they need to have the same number of electrons first, right? Otherwise, you can't have the same electron configuration. So I have to remove an electron from lithium. So if I remove an electron, make that a 0, I removed one electron. So this now has to be lithium plus. These are now isoelectronic. Helium and Li plus are isoelectronic. So you can kind of see it. If I take one electron away from lithium, I'm at helium. All atomic ions of groups 1, 2, and 7 are isoelectronic with a noble gas. Noble gases have extremely stable electron configurations. So when you make ions, remember ions, you're either gaining electrons and making an anion, or losing electrons making a cation. They're all isoelectronic with a noble gas. Let's try playing this isoelectronic game. Write the neutral element, so I mean that is no charge, that is isoelectronic with each. Magnesium ion. So here's magnesium. It's plus 2, so you have to lose 2 electrons. So that means magnesium has 12 electrons, lose 2, you're down to 10. So 1, 2, you're down to 10 electrons, that's neon. So that's why magnesium only loses 2 electrons, because then it's isoelectronic with a noble gas, a very stable electron configuration. Sulfide. Sulfur has 16 electrons, but we have 2 extra, so that means you have 18 electrons, or just give it 2 electrons, 1, 2. Argon. Check this out. Iron 3. Iron has 26 electrons. We have to lose 3. So that means we really want 26 minus 3, 23 electrons. Well, what has 23 electrons? 1, 2, 3. Vanadium. Vanadium has 23 electrons. Iron 3 and vanadium are isoelectronic. Order the elements, fluorine, strontium, magnesium, and phosphorus, in order of increasing size. So here's fluorine, strontium is way over here, magnesium, and phosphorus. So strontium is definitely going to be the largest. Fluorine is going to be the smallest. How about magnesium? Magnesium is pretty close to strontium. Phosphorus. So there's my increasing size. How about increasing ionization energy? Remember, size and ionization energy are just opposite trends. That was size. Ionization energy was just the opposite direction. So let's just reverse our order. Increasing ionization energy means the largest atom will have the smallest ionization energy. So we have strontium, magnesium, phosphorus, and fluorine. Order the elements in order of increasing size. Kind of a trick question, because check this out. They're cations. So the higher that positive charge, the smaller it's going to be. So we'll have carbon 4, and the carbon with the 3 charge, carbon with a positive 2, and the neutral carbon atom has the most electrons, so it's going to be the biggest. Again, ionization energy has the opposite trend of size, so let's just flip our order around, and we'll have increasing ionization energy. Carbon, carbon plus 2, carbon plus 3, and carbon plus 4. And it makes sense because the highest ionization energy is the one that's the most positive. It's going to take a lot of energy to pull an electron, which is negative, away from something that has a positive 4 charge. Order these in order of increasing size. Same idea. The smallest is going to be the one with the least electrons. The largest, one with the most electrons. That means chlorine would be in the middle. Increasing ionization energy, opposite trend of size. So chlorine plus will have the highest ionization energy. Write the neutral element and its corresponding electron configuration using noble gas core notation that is isoelectronic with each. So what neutral element is isoelectronic with these guys? Bromide. Here's bromine. It has a negative 1 charge, so 1 extra, 36 electrons. That's krypton. And write the noble gas core notation for krypton. Well, I'll just put krypton in brackets. Calcium. Here's calcium. It's calcium ion. You have to lose 2 electrons. You get 18. It's argon. Noble gas core notation, argon. So try these. See if you get the same answers as me. We're going to lose 3 electrons for aluminum. That bring it down to 10. It's neon. Oxide. You have to go from 8, 1, 2 extra electrons. It's neon. Cadmium. Here's cadmium. You have to go to 46 electrons because we're losing 2. That's going to be palladium. Then we have to write its noble gas core electron configuration. So that's go backwards to krypton. So we're here. It's going to be 5s2, 4d1, 2, 3, 4, 5, 6, 7, 8. 48. But remember the trick. Make D10 and D5 when you can. So definitely, so this is wrong. We need to do krypton, 5s0. And you can leave that part out if you want. I kind of like it there. 4d10. Manganese. Manganese 2. Manganese is 25. Lose 2 electrons, you're going to be at vanadium. So what's vanadium's noble gas core notation? It'll be argon. (4s2), 3d1, 3d2, 3d3. Again, take a look at it before you move on. Can you make D5 or D10? You bet. So this is the wrong answer. It should be argon, 3d5. There are a couple ideas here. One is this idea of isoelectronic, and atoms form ions. Either they lose electrons or they gain electrons. And they're going to lose or gain electrons until they get the electron configuration of a noble gas. So these ions, whether they're cations or anions, they're almost always isoelectronic with a noble gas. The other things to keep in mind are these trends. And be familiar of how electronegativity, electron affinity, and atomic radius increases across a periodic table. And you should be fine. Good luck.